Let's look at the example 10.2. Out of this example, we want to use the least square technique to find the equation of the line that runs through the following data points. Again, the keyword is the line. So we are looking for a linear function. A linear function in the general look is the equation a plus bx. Okay, so we're looking to find a linear function that can be used to approximate the data in the table in such a way that we can minimize the square of the error. Okay, so when we want to minimize the square of the error, that technique is called the least square technique. So out of this example, so it is the same as example 10.1, but the difference is only that we have more data points. We have 10 data points altogether. But the system of normal equations, since we are looking for a linear function, so the look of the system of normal equations will be exactly the same as previous problem. That means our system of normal equations will consist of two variables and two equations. Let me bring you back to the previous example so that you see what I was talking about. So in example 10.1, when we was trying to find a linear equation a plus bx, so at that time I constructed that system of normal equations. So you could see that that is a system of 2 by 2 equations, 2 unknowns. So it will be the same because there are two constants to be determined, a and b. But it's just that we have more points involved in this case. So I constructed the table for you already. In the first column, I put the I number in there. Second column, I put all the values of xi from the table. And second column, I put all the values of yi. And I did also find the sum of xi, the summation of all the values of x in that column. And also I did find the sum of all the yi values. Okay, the system of normal equations needs also summation of summation of xi squared and summation of the product of si and yi. So the next column of my table, I computed for you guys all the xi squared and then add them all up. And also this column contains the product of each xi and yi, and then I added them up below here at the bottom row. I leave the other two columns as blank because in order to get the approximate value of each xi by using that polynomial of first degree, we have to solve the system of normal equations first. And also to find the error squared, we have to get the error. The error is the difference between the true value, which is the column y, and the approximate value. So you cannot find the error square if you don't know the approximate value of each of xi. So the look of the system of normal equations, I'm going to be writing it in the matrix form. The system of normal equations. I'm going to be writing it in matrix form. So that is n. N is number of data points. It will be 10. I'm going to replace it with 10 later. And that spot, it's summation si I run from 1 to n. And in this case, n is 10. Okay, how about I just go ahead, write n as 10. And this n is 10. So that is summation si I runs from 1 to 10 as well. And that spot is summation of si I runs from 1 to, that is xi squared. Multiplied by the column vector that has a and b, the constant that we have to find out. And on the right hand side, summation of yi, and again I run from 1 to 10 because there are 10 data points. And the last spot is the summation of the product of si and yi, and I runs from 1 to 10 as well. So your matrix, you just bring all those values down here, so 10 goes here, 45 goes there, 45, and that spot is summation of SI squared, which is 285. 285. And you put that vector right down. Summation of yi is 120. And then summation of SIYI is 702.5. So this is the system to be solved for the constants A and B. Okay, so you can use Gaussian elimination. I'm going to be writing the augmented matrix. I show you the way that you really have to show it when you do the final examination. And we will be doing the final exam online, so you really need to show the details of your work. Okay, it's not okay with me just writing the system and then you just say, hey, this is the answer. You have to show the work in detail, because I cannot force you not to use the computer when you do your exam online anyway. So I'll just try to ask you to show each step in detail. For example, if you want to solve the system by using Gaussian elimination, you have to show me write down all the steps in using Gaussian elimination to solve the system. Like this one, I need to divide the first row by 10, and I have to say so. That divide the first row by 10 to get the first row that is changed to 4.5. Oh, I put that column wrong. I need to put the right hand side, not the variables A, B. So 120, and that is 702.5. Okay, 120 divided by 10 is going to be 12. And the second row remains the same, 45, 285, 702.5. And then this is your leading one. You use it to get rid of that 45 by performing R2 minus 45 R1, R2 minus 45 R1. And then the resulting matrix is going to be an upper triangular matrix, and you can use back substitution to find the values of A and B respectively. 0, and that is going to be 82.5, 12, and 162.5. Okay. Out of the last row, you can find B immediately by dividing of the both sides by 82.5. You can get B, and you're going to get B as 1.97, and your A. Okay. So out of the second equation, you can get B. By knowing B, you put in the first equation right at that spot, because that is the coefficient of your variable B. You can find A immediately, and your A is going to be 3.14. Right after you've got A and B, then you get that first degree polynomial. Then P of X is going to be 3.14 A plus BX plus 1.97 times X. So this is the look of the linear regression polynomial. Okay, first degree polynomial that you obtain the coefficient A and B by using the 10 data points given with the table. Right after I've got that approximate polynomial, I will be using that polynomial equation, or you can call it as polynomial regression, linear regression, polynomial, whatever. Okay, you use it to approximate the future value of y at some x. All right, so I'm going to be putting or evaluating. So you go back to the table, and then now you can fill in that table by evaluating by using that P. Let me copy that P. I'm going to copy that and go back to the previous page, put it above it, because we'll be using this guy to evaluate P at each xi. So if s is 0, then your P will be 3.14. You put that down, 3.14. And you do the rest, okay? You do the rest. Find, plug x in that equation as 1. You can find P at 1. P at 1 is going to be 5.11. P at 2 is going to be 7.08. And then keep moving down. Just use that function to evaluate the P at each x. X is in the second column. So 9.05, 11.02, 12.99, okay, 14.96, 16.93, 18.9, and 20.87. I got this column by using Microsoft Excel. Actually, using the technique of least square regression is very easy to write the code in Microsoft Excel. You can find the sum each column easily, and also you can evaluate the polynomial at each xi easily by using Microsoft Excel. Alright, so out of the last column, because I need to find the square of the error, so the error at each row is going to be the difference between the exact value, which is each yi, and the approximate value, which is p at each xi. So out of this spot, you're gonna have 3 minus 3.14, and then you square it, for which you have 0.0196. I'm gonna be copying all this down. I use Microsoft Excel to do it. Okay, 0.8464, and then 2.4025. You can double check. I could be wrong in all those spots. Okay, I recommend you to double check every spot yourself by trying to use Microsoft Excel to evaluate each spot. 0201, 1.0816, 1849.16, 0.0169, and then the summation of the error square is 6.9245. So the summation over here is the total sum of the error square. You add this column together to produce that the summation of the square of the error. So by using this technique of least square regression, that is the minimum value of the least square error. Okay, so is that only one question out of that example? It just say use the least square to find the equation of the line. We got the equation of the line, then we are done, and that is the answer. Okay, so in the test, it depends on how I ask you to do. If I only ask you to find the equation of the line that runs through the data points, so you can actually stop over here. You don't even have to fill in the table. But if I provide you the table, or if I say in the sentence of my question saying that you have to compute the sum of error squared, then you have to have those two columns in your table. All right.